Alright guys, hello, welcome back. So we're gonna discuss today perhaps the most important point in principles of flight, that is lift. Alright, so first thing we need to know, how is lift generated? Lift is generated by the difference between the pressures over an aerofoil, upper and lower surfaces basically. Okay, so this is how lift is generated, and lift is perpendicular. Lift is perpendicular to relative airflow or flight path or drag. Okay, so the most appropriate is relative airflow, and then you may have options like flight path or drag. Okay, and it is governed by this equation, that is L equal to CL half rho V square S. Okay, and CL is your coefficient of lift. Okay, rho is the density of air. V square, or V basically, is TAS, true airspeed of the aircraft. Okay, and S is the surface area. We need to know that CL, that is coefficient of lift, depends on camber and angle of attack. Okay, so this dependency of C of L on camber of angle of attack will lead us to this equation, L equal to CL half rho V square S, where this is dependent on camber and angle of attack. Okay, so now I want you to know is, when a aerofoil is manufactured, largely the camber is kept constant and the surface area is kept constant. It's a different thing that we have when we have high lift devices, both change, but on a simple aerofoil without any change of flaps or any surfaces, the CL, the camber and the surface area remains same. Alright, so now we'll discuss something important, that is, just note down this table. Okay, altitude, TAS, IAS, and overall change. Okay, so if your altitude is greater than mean sea level, MSL, your TAS will increase. Okay, and overall TAS will be higher for a same IAS. On mean sea level, both will remain same, TAS equal to indicated airspeed, and below mean sea level, your IAS, indicated airspeed, will increase. This will lead to TAS less than indicated airspeed. This whole thing is your IAS, or dynamic pressure. On the previous page, I remember I told you this is TAS, but the whole thing together becomes indicated airspeed. Okay, so now basics, we'll start from, suppose if you have a high camber you'll get low speed but high lift. And if you have less camber, you will get high speed. That is what high speed aircrafts have, high speed but low lift. Okay. And generally we use asymmetric aerofoils, because symmetric aerofoils, if you remember in the previous video, symmetric aerofoils is something like this. When the chord line and the camber line coincide, it's a symmetric aerofoil. So these days aerofoils are designed as asymmetric because asymmetric aerofoils give lift even at zero angle of attack, and little beyond as well they give lift. And in symmetrical aerofoil, only when the angle of attack is positive, only that is when they generate lift. Alright. And speeds, varying on the speeds, we have aerofoils as subsonic, that is less than 0.8 Mach. Alright. Transonic, 0.8 Mach to 1.2 Mach. Supersonic is 1.2 Mach and beyond. And there's something called hypersonic, which is under development, is greater than 5 Mach. Alright. So these aerofoils are on basis of speed are split into these types. Okay. So now we'll do equations, how the equation reacts to different changes. Okay. Before that, simple thing I would like you guys to know is formula of TAS. TAS equal to RAS, rectified airspeed or calibrated airspeed, plus 2.2% of RAS per 1000 feet. Okay, this is how you calculate the TAS. Okay, so now we'll discuss the equation. Lift equal to CL half rho V square S. Say, suppose for a constant lift, alright, for a constant lift, as the altitude increases, obviously the density will decrease. So it has to be automatically compensated by the increase in TAS. Alright, if other parameters remain constant, that is camber and angle of attack, others all constant, if altitude increases, your TAS has to increase to compensate for the lift, loss of lift. So that sense you will have a constant lift. For example, say at 40,000 feet, the density is almost 1/4. Okay, so at that point the equation turns out to be L equal to CL half rho V square S. Since this has become 1/4, this has to become 4 times. The TAS has to increase by 4 times to maintain constant lifts, keeping other parameters all constant. Okay, so if you at 40,000 feet, you have to 4 times the TAS to keep a constant lift. So this is the application 1 of the lift equation. Okay, so let us consider another situation. Lift equal to CL half rho V square S. Okay, in this case, camber, in all the discussions which I'm going to do now is with camber constant and surface area constant, so don't worry about it, we'll do it in the high lift devices. And angle of attack. So in this case, at a fixed altitude, okay, where the density won't change, if speed is increased or say decreased, depends, whichever, if the speed is decreased at a constant altitude, I told you right, constant altitude, then to maintain constant lift, the angle of attack has to be increased or decreased. In this case, if you increase speed, your angle of attack has to decrease. Alright, and if you decrease speed, your angle of attack has to increase to maintain constant lift. So this is application 2 of the equation. I hope this is clear. Alright, so now let us go to a third application. Lift CL half rho V square S. Camber angle of attack. Keeping these parameters constant. Okay. Now, as the altitude increases, alright, when the altitude is increasing, the true and if the altitude is increasing, your density is obviously dropping. Okay. But if the true speed is kept constant, okay, if the true speed is kept constant, the amount of airflow flowing over the wing will obviously decrease, and hence the lift will decrease. So if the true airspeed is kept constant and you're climbing, basically when the density is decreasing, you're climbing, the lift will also decrease because the airflow, amount of air flowing over the wing has reduced. Alright, so this is the third application. Okay, last and final one is a tricky one, an important one as well. Okay, so let us discuss that as well. Fourth one. Okay, so lift equal to CL half rho V square S. This case says that, okay, so camber and angle of attack kept constant. If the dynamic pressure or the IAS, indicated airspeed, is kept constant and the angle of attack is also same, it is kept constant. Okay, it's kept constant. Planes, even though they are flying at different altitude, will produce same lift. Okay, so for example, if a plane is flying at 40,000 feet and a plane is flying at 10,000 feet, okay, if the indicated airspeed is kept constant, alright, if the indicated airspeed is kept constant, IAS, the whole thing is kept constant. So if that is in case, if this is increasing, this will decrease. So this, the whole figure will be kept constant, and angle of attack is also remaining constant. If this both are constant, the lift will be remaining constant. Now this comes from here. Suppose you're above mean sea level, alright, and you're climbing, so naturally TAS will increase. Alright, so TAS will be greater for a constant IAS. TAS is increasing, so for an increasing TAS, the density is obviously decreasing. So hence, if this figure is constant, this angle of attack is also remaining constant. The lift will be constant at both the levels. Alright, I hope this is clear, and this is a very tricky and important question that comes generally in exams. Okay, so now we'll discuss the graph coefficient lift. I did it in the previous video as well, but I'll just draw it again. Okay, this is much more practical. Last one we drew was theoretical one. This is -4, 0, and say 4, and approximately here we have say 15 to 16 degrees. At 0 angle of attack also we have some lift generated. At -4 we have 0 lift, 0 and further. Alright, and this is the position CL max. Almost the value is almost 1.52 is the standard value that is for CL max, and CL is the measure of lifting effectiveness. So what is CL? CL is the measure of lifting effectiveness. Okay, now if greater the CL and lower the speed, okay, V square, lower the speed, a given lift can be obtained or maintained constant basically. For example, let us write the equation half rho V square S. Okay, so camber, angle of attack, and CL. If CL is increasing, CL can increase only when you increase the angle of attack, because camber is generally fixed. I mentioned when the start of the video we'll be discussing only without high lift services. Okay, so angle of attack is increasing, your speed will decrease, and this will keep your lift constant. Okay, few points to note down. So 0 degree of angle of attack, you have positive CL. As you can see, climb coefficient of lift is positive. 0 to 12 degrees, steady increase of CL. As you can see, it's linear from 0 to approximately 12, and 12 degrees to 15 degrees you have a lower rate of increase of CL. CL is increasing but at a lower rate, and greater than 15 you have a rapid decrease in CL. Is that clear? This point where there's a rapid decrease in CL, this is an important question generally that comes out, is called critical angle or stalling angle or your bubble point. Okay, critical angle, stalling angle, or your bubble point, where the air bubbles and breaks, the smooth flow is lost. Okay, now there's something called as lift transducers. The spelling is LIFT, transducers. These help in measuring lift or angle of attack. So basically it is fitted in modern heavy aircraft at the leading edge of the aerofoil or the wing. It measures the lift or the angle of attack, and by electrical sensors basically, and it serves also as a stall warning system which converts pressure energy into electrical signals and gives an input into the cockpit. Alright, so for asymmetrical aerofoil, earlier we just written here, this is for an asymmetrical aerofoil, from -4 to around 15 to 16 degrees the CL increases and there's a rapid drop. Okay, now we'll discuss effective high lift devices. The ratio between lift and drag we'll discuss in the next video, so that we can, after finishing drag, so that we have an idea about drag and then we don't get confused regarding it. Okay, so high lift devices, what are high lift devices? They are generally flaps, slots and slats. Okay, so these are high lift devices. Now what are they used for? They're used for reducing takeoff and landing distance. Okay, and this is crucial, and this is also crucial, they increase CL max. I mentioned the CL max is the point at 15 to 16 degrees. Okay, CL max at a reduced speed. These are two important uses of the high lift devices. So the graph, I'll show you the difference between the graphs. So say a normal graph, if you remember, is something like this. Okay, this is say 15 degree point, but what high lift devices do is they generate lift like this. So your earlier CL max was somewhere here, now the CL max has risen. Okay, angle of attack. So when you extend the flaps, slots and slats, they increase the CL max at a reduced speed at the same angle of attack. So this is with the flaps and this is the clean configuration. Okay. And stalling speed also, if you extend high lift devices, the stalling speed also decreases, so it's an advantage. Though the drag and all increases, we'll be discussing in the next video, but during the landing and takeoff, your stalling speed decreases and the CL max increases. Alright, so I'm going to read out few points about lift summary, so you guys can just listen to it. Lift must be balanced by weight in straight and level flight, so at any given time both weight and lift required are constant. To maintain constant lift, if density varies with altitude, a constant IS must be maintained. If altitude increases, then density decreases, and then TAS obviously increases. Alright, so to maintain constant lift, if speed is changed at a constant altitude or density, the angle of attack must be adjusted. We have discussed all these points. If speed is increased, angle of attack must be decreased. Alright, so then already we have discussed about lower air density, and just once let me just write down this thing is important, you guys note it down. So rho is proportional to static pressure, that is density. Rho is inversely proportional to humidity. Rho is inversely proportional to temperature. Okay, if you have low air density, not density altitude I'm talking about, if you have low air density at the airfield, then you will have a longer takeoff run. This is a key point to remember, please note it down. Low air density will give you longer takeoff run, and high density altitude here I'm talking about will give you poor performance. Okay, and VMT is proportional to the weight. We'll be discussing this in the further chapters. Minimum drag speed, this is called minimum drag speed, is proportional to the square root of weight. Alright, so that's all about lift. If you guys watch this video again, I hope the lift chapter is clear. So any doubts, please let me know, comment below, like it, share it, enjoy it. We'll come back for the drag video. Alright, bye bye.